Supposed to start 10 past. I see there's some people rolling in. I think I'm just going to talk for a bit and let you guys take a seat. It's very nice to see that so many people showed up for my talk about creative analogies in deep learning. A lot of people think of deep learning and all this stuff as a hard science, and I think that the soft stuff is what's most often forgotten. I'm not sure if it's a made-up story, but Einstein supposedly said that he came up with his theory of general relativity when he was trying to imagine what it was like to be a photon, traveling through space. And I hope to show that, you might think that of course he can say that, he's a genius, but there's more to it than just that. His ability to really imagine things in more than just hardcore math is probably what let him do what he did, but he was also extremely good at math. So, with that being said, let's go on to the talk. Actually, I'd like to take a little poll here. How many people here have made their own models with Keras and TensorFlow and that kind of stuff? Great. Okay, it's going to be much more interesting. Otherwise, I'm going to have to do a flame war because that's the only way to get people going. All right, so I'm going to talk a little bit about why deep learning works and why it's good. And I have a computer science background. I think of myself as a hacker, not especially good at anything. And the people that I compete with, so to speak, are statisticians who claim deep learning and machine learning as their own. So I need to sort of set things in context and have a computer science aspect to it. So what's special about deep learning? You might have heard people say there's nothing new about AI and deep learning. It's just statistics plus GPUs. Or now we have lots of data, and we didn't have any data back in the early 2000s. Or some other reason why deep learning is nothing special. Well, deep learning is pretty special. So we're going to talk about deep learning and compactness. We're going to talk about this chasing the photon thing, except we're going to be chasing the lost spaceship, as I tend to think of it. And we're going to talk about how you can use these types of ideas to solve really hard problems. That's it. That's all my slides. So let's get to the nice part here. I hope this text is big enough. And we're going to get going. In case nobody's seen this way of programming, this is a notebook. It's essentially just a web interface to your programming language so you can share stuff with your friends. It's pretty convenient. Okay, so I'm going to be exemplifying with a language called Julia. Julia is a pretty new, up-and-coming language that's especially well-suited to scientific computing, numerical computing, because it has the ease of use of Python, but the speed of C. And how does it do that? It's JITted, and it has a very cool type system. So I'm just going to give a couple of examples here. This is going to be your intro. It's like Python, simple. You don't have to typecast stuff. You can make a random array. You can multiply them. And as you can see, here's a little macro. You can look at your function and see the assembly code. You can see that in this case, it's taking the float values and using some simmed acceleration, so it's fast. All right, that's the introduction to Julia. Actually, there's one more thing I'd like to show, which is that Julia is really cool for doing symbolic stuff, sort of like Lisp. And this is probably the code that I'm most proud of right here. And so when you run this macro here, it returns another smiley that's not in the macro, which I'm pretty happy about. OK, so I don't really need to talk that much about Julia. You'll have to take my word for that it is really blazing fast. I mean, like 2 orders of magnitude faster than Python. And so it is important because you're working with TensorFlow or something, and you're like, I read in a paper that there's a new activation function. I want to try it. Oh, it's not in TensorFlow. OK, well, the math is simple enough. I know how to implement it. I need to do it in C++. And then you want to stab your eyes. So with Julia, you don't have to do that. You just stay in Julia. Everything's in Julia. I was having a panic attack just a couple of minutes ago because this JavaScript stuff wasn't working here. When you have to juggle like 12 languages just to get your stuff done, it's a little bit of a pain in the butt. So, Julia. All right. I didn't introduce myself. My name is Robert Luciani, and I own a company called Laketide that does big data and machine learning consulting. So we tend to do a lot of custom projects for clients, and people often ask us, what our favorite machine learning framework is. And we like a lot of tools, and we use the best tool for the job, so there's no single best tool. But for a lot of the work we do, we use a framework called Flux. And it's not really a framework as much as something that keeps track of gradients. It doesn't really do anything. And I'm going to really show you from the basics what deep learning is using Flux. So I'm just going to import Flux here and plots so we can draw stuff out. I hope this doesn't hurt too much, but we're going to go back to the stuff that we learned in high school. As you know, this is a nonlinear equation. You have a little squared there, you have a little x there, and a plus. This is how you draw equations, and as you can see in Julia, it's fairly simple. You can define your function, and if you send it a 4, it'll go through this equation, give you the result. Now, what you can do with Flux is Flux keeps track of the gradients of your equations. So you have an equation that is a curve like this, right? So let's say your speed, and you can calculate your acceleration at a certain point by drawing a straight line onto that curve. That's what it does. So you can use the gradient function that's built into Flux, and as you can see, the gradient of 3x squared 2x plus 1 is 6x plus 2, if you recall it. And so if we run it, we'll get the gradient calculated. You can even take the gradient of the gradient and calculate that by sending in df, which we defined up here, and send that as an argument. And you'll see you'll get out 6. So why is this useful? Well, deep learning and all of machine learning is about tracking changes. So Flux does this a little bit conveniently for you. Instead of having to write gradient for one parameter, you can just write param, and it'll keep track of the gradients of everything. So if I make a little array that's 2 by 4, it'll keep track of the gradients for all those values. And in deep learning, you can have millions of parameters, so it tends to be convenient. And what I have here now is a variable x that has, it's not a variable anymore, it's a struct, and it has a couple of things in it. It has the data. As you can see, it's the same as the one above. And you have the gradients for the data, which is 0 right now. So what can we do with this? Let's start by solving the original problem. Neural networks, rightly, as statisticians say, were invented a long time ago. And one of the first dilemmas people realized was that you couldn't use them to solve the XOR problem. Now, what is XOR? An XOR is a logical gate where if you have true and false, it'll return true. Otherwise, it'll return false. So if we run this here, you'll see that the true return false, the false return false, and the other two combinations return true. Why is this significant? Well, you will see very shortly. I want to show here also that you can do it with ones and zeros. It's the same in principle. Let's draw it on a plot to make it a little bit clearer. If we put, oh gosh, this stupid plot program. If we put the dots on a plot, the question here is, you have an equation, a linear equation, and your task is to classify these dots. In other words, draw a line here somewhere such that all the blue dots end up on one side of the line, so you can classify it as left of the line is true and right of the line is false. Well, as you can imagine, there's no way for you to arrange a line here such that all the blues end up on one side and all the oranges end up on the other. How do we solve this? And back then, the statisticians told you, flipped the table, and it became known as the AI winter. Well, it wasn't quite that bad, but we didn't have as many tricks as we do nowadays for deep learning. So if we draw a straight line, as you can see, there's no way you can rotate this to split the dots between true and false. Now the question is, if you wanted to split them, how would you do it? The funny thing here is if you ask a kid to split it, well, they would take a pen and they'd be like, they would draw maybe a line like that. And so they wouldn't even use a straight line, of course, because they don't know what a linear equation is. But it's actually more profound than that. If we draw a nonlinear equation here, we square the x, you'll see it starts to get curved, and you're like, okay, maybe that kid wasn't so dumb after all. What if we can make it curvy enough that it can sort of go around the blue, behind the orange, and then around the other blue? Okay, I don't know what that equation is, but that's why it's called machine learning. It can learn it for you so you don't have to learn it. So let's go ahead and see if we can do that. Let's create two random vectors of trues and falses, A and B. Just mush them together like that. And we can create what the XOR of those two values would be. So as you can see, false and false would be, let's see, this wasn't very good. Let me randomize it again. The Boolean randomizer isn't super good. Let's go and see if we can get, here we go, some better ones. All right, as you can see, false and true become true, true and true becomes false. All right, it's as expected. We have a 10,000 long set of values that we can train our machine learning model on. Now, we're not going to cheat and use some kind of framework. We're going to do it with arrays, because that's the awesome way. And we know that there are, in deep neural networks, there are hidden things in the middle. There are hidden neurons. All that really means is how wide the array is going to be. So we're going to say that this array is 4 wide. Now, here comes the intuition. What does that really mean? The array that we had a little bit further up was 2 wide, because it was 2 values going in. So in effect, we're making it twice as wide. We're giving it twice as many parameters to work with. Let's see what the result of that is. Here we're saying we want to have a random matrix that's 4 wide and 2 tall. Param, remember from Flux, it'll keep track of it, and a bias, because you need to have the coefficient and the bias that you add. And as you can see, here's the regular linear formula. We're going to call this the fully connected neural layer 1. And then further down, we'll have the fully connected neural layer 2. Let's go ahead and write these matrices. And we also have something here in the middle that I wrote that's connecting these 2 matrices, ReLU. I'm going to plot one kind of function called a sigmoid function, and it looks like this. And if I plot the ReLU function on top of it, you'll see it looks like this. Okay, so back in the 90s and early 2000s, they didn't have the rectifier activation. Anybody that plays guitar knows what the rectifier is? This is a rectifier. Rectifier is where any value above 0 comes in, output that value. It doesn't sound very profound, but until you've tried every single thing and figured out that this is the good way to send values from one neural layer to the next, you can't train a deep neural network. It'll sort of die halfway through, which is why they couldn't train networks that were deeper than a couple of layers. Okay, so now we have rectifier activations, and in this network that we had above, that's 2 layers, fully connected 1 and fully connected 2, I've connected them using a rectifier unit, which means that the output of the first layer, if it's greater than 0, it'll continue on onto the next layer. That's all it means. And then I have a function at the end called softmax, which really is just saying which of the 2 outputs is the strongest, because I want to have a true and false output, since that's what this problem is. But you don't have to have a softmax. If you don't have a softmax, you will get a numeric value, as we will see shortly. Okay, so we have our little neural network here. We can try it. You see, we get 2 outputs in terms of statistics. The neural network right now is pretty sure that true and false becomes true. It just happened to be that way because these values are randomized in the beginning, so it was good randomization for us. In fact, it's very important that networks are initialized randomly. But all right, here we go. I'm going to define 3 more functions that are not super important to understand, except for perhaps cross-entropy. Cross-entropy is the way we're going to score our output. So we get an output from the neural network, 2 values. Are they good or not? Well, cross-entropy is a way of saying, if you had guessed, how high is your chance of having guessed right? So it's an information theory type of thing. We have the true answers that we created before, and we have the output of the model. And then we're going to calculate the cross-entropy between the 2 and say, yeah, you're pretty good at guessing now, so you're going to get a high score. That's what cross-entropy does. Okay, let's go ahead and run that cell. And the last thing we need is the thing that they didn't know until the late 90s, which is backpropagation. Backpropagation is, let's say the model is bad, which it is. You need to go back and correct it a little bit. By how much? By 0.1. So you have the gradients, and you see that it's going in the right direction. Keep pushing those values until it starts getting better and better and better, until it doesn't get better anymore. That's what this function does. It takes the data and the gradient and then adjusts it a little bit. So let's go ahead and loop over that adjustment process 1,000 times using the data that we have, x and y. Let's see here. I don't remember if I wanted to run this many times or just one time. OK, accuracy, perfect. So this neural network seems to have learned how to split x and y, something that the single layer neural network couldn't do. And what is it that it's doing? Well, first of all, let's just try it on true and false. OK, now it's almost 100% sure that true and false equals to true, but not entirely. It's 94% sure, as you can see here. OK, let's go ahead and draw and see a little bit. If you remember, this is what the XOR looks like, and you need to be able to draw something on it to split the two. And what we did was we gave it twice as many parameters, which means now it has 2 lines it can use to cut these things apart with. How did it choose to draw those lines? Let's go ahead here. Well, that makes quite a lot of sense. Obviously, if you get to draw with 2 lines, it's very easy. Chop, chop, and now everything that's down here is false, everything that's up there is false, and everything in the corners becomes true. And it will always be right, because we're just dealing with binary values. But this is where deep learning is different from parametric learning. Deep learning doesn't just do more linear stuff. It does nonlinear stuff by going deeper. So the width of the network is roughly equivalent to how many lines and how many parameters you have. But the depth of it has to do with the nonlinearity of it. I think it's easiest if we exemplify. Let's go ahead and give it a little bit more complicated data. It's basically XOR, but a little bit more complicated. This is what data looks like in real life. Many parameters, many values. You see that there are a couple of values that are crossing over into the other side where they shouldn't be. Let's see if our model can learn this. Of course, Flux has a couple of shorthand things, but not very many. This is maybe something that you might recognize from real deep learning frameworks. So instead of having to write the matrix by hand every time, I know what goes into the matrix, and I do the same thing every time. So I can just write dense. That means that the matrix is 2 by 10 wide, and it ends with a rectifier activation. And I can stack them like this. So here, this one is 10 wide because the one before it ended with 10, and then it gets thinner. So you can imagine it as a network that's wide, that sort of gets funneled down, and has 2 little outputs that go into the softmax, so I can get my statistic of whether it thinks it's true or false. I also use an optimizer that's a little bit smarter than just always going forward the same step at the same time. I use an optimizer that looks at the gradient, and if the gradient is very big, go quickly, and if it's going upward, have a little bit of momentum so that you can get over a hill and that kind of stuff. We'll see in just a moment what that means, hill. I'm thinking about it in terms of spaceships, but soon you will too. The loss, you'll find the cross entropy again, accuracy so that we can print how good it is, and let's go ahead and train it. We'll just train it one time instead of doing it many times, and let's see what it learned. This one is a hit or miss. OK, it's not so bad. It could be better. OK, what we have here is essentially 2 round lines, like I was talking about, like the child might draw, dividing the true and false. This is like a hyperbolic type of line that goes out towards infinity. And it's something that the deep learning can do. Now, what is special about this? You might hear statistics people say that deep learning is just optimization. You can optimize using pen and paper if you want to, but that's not what's special about deep learning. What's special about deep learning is that because you have the depth, under normal circumstances, I've written it best here, consider that you have something you want to classify, and there are k classes. If you want to make it wider, you would have to have n times k observations in order to learn that thing. Whereas with n times k observations in order to learn that thing with deep learning. With a parametric method, you would have to have an exponential number of observations. And it's the same thing with the number of parameters. So whereas you would need to have maybe 1 million parameters in width in order to learn something with a parametric model. With deep learning, for every halving of it, you can add one layer. So you can imagine how compact this network can become. Whereas you started with a network that was 1 million wide, you can make it half to 500,000, and it's 2 layers, half to 250,000, and it's 3 layers. And suddenly you have a manifold or a compact representation of a very complex phenomenon. Okay, so what do you have in the network? At the bottom layers, this is what's important. You have a representation of something. The neurons at the bottom of the matrix, when they output something, those are representations of those curvy lines. So if you think of, for example, a cat classifier or a dog classifier, any kind of image classifier, the neurons that are at the very bottom embody the formula, embody the essence of catness. And it's a very big formula, so you might never be able to write it down. But in essence, it has kernels, activations, and everything. And when you have all of those together, you can actually backtrack it a little bit and find a kernel that is specialized at detecting edges and shapes that are exactly like cat ears. And a cat always has 2 cat ears. And those 2 neurons need to be activated at certain distances from each other. And so it's like when you would tell a friend, what's a cat look like? Oh, a cat. This has got 2 pointy ears, has a funny mouth, and so on. Those neurons, in essence, exist at the end of the neural network. That is the essence of catness. So neural networks don't learn values, they learn representations. And anything you can conceive and represent in your mind is something that a neural network can also potentially learn, which is why neural networks are called universal function approximators. So what does it take for a neural network to learn something? A neural network needs to know the difference between what it's guessing and what it's supposed to guess. That is the essence of learning. So you make a bad guess, the person says, it was okay, but really you should be more in this direction. That was the truth. And we do this with the loss function. So I'll jump to my next slide here. The loss function for humans. Does anybody care to take a wager what our loss function is? Our loss function is death through natural selection, right? So we make a bad guess. I can totally make that jump. And the next iteration improves. There are other types of loss functions that are super interesting. Consider a beehive. There are not very many animals that are suicidal, but bees are among the few. And that's because all the bees that can sting you are female and are clones of each other, meaning they all have the same DNA, meaning if you kill one, but it benefits all the others, that's a very good gene for that bee to have in it. So it's very good for it to sting a bear or whatever if it saves the nest. So the optimization strategy for bees results in that suicidal behavior. So the same thing with neural networks determines how well and how fast they can learn. Now, back in the old days of stats, Carl Gauss, one of the geniuses, invented something called mean squared error to calculate how the planets were rotating around in the solar system. And mean squared error is basically like, Pythagoras' theorem. It's square minus square, and then the root of it, and you can calculate the distance, how far off you are. And the good thing about squaring stuff is that the result is a Hilbert space, which means it's all connected, which means that somewhere in this space of errors, let me back up a second. Let's say you have 2 values that are the input, x and y. And you can sweep through these values, big X, big Y, big X, big Y, and you graph that. And then when you think about the depth, that's the error. There's a sweet spot with the X and the Y where the error is very small. And that's where you want to end up with your machine learning model. So the task is really to sweep through all the parameters that exist in these arrays and try to find the combination of all those parameters such that the error, the output, is as small as possible. So there are some parameters, obviously, where the error is infinite or huge, and others. And so you want to keep going downwards to get the lowest amount of error. And a lot of people imagine this before we had the tools for it, back in the 90s, as being very similar to the way people imagine energy in quantum physics. So you have, now it's round, but it could just very well be square. Imagine you have your parameter x and y, and then somewhere in the middle there's a sweet spot where you want to tune the network such that the error is very small. But this is not what it looks like in practice. And a lot of people learn this because they start to train their neural network and it just doesn't learn anything. You're like, what the heck? It's supposed to be able to do this. And so in my case, well, it can look like this, for example. It starts to learn and then it stops. Why? And people that have worked a lot with deep learning really have built an intuition for this, which is why they were able to guess that this was what things looked like, but we never had pictures of it before. So, you know, it would start learning, and then people developed something called descent with momentum, so that if it went into that little moat there, it would have a little bit of momentum so it could get unstuck and keep going down towards the global minima. But more often than not, you have these really weird things. You're like starting, and then you end up in a little place, and you're like, oh, it's learning. And then it sort of stops learning because it needs to make its way down that little snake path before it can get to the global minima. There are really weird landscapes, and it's hard to know exactly what they look like, especially when your networks are really, really huge. And this is what people noticed when they started making networks, because they got better and better scores, and it took longer and longer to train. And then, you know, they're like, okay, twice as big network gives me twice as good score. Let's make it bigger. Now we have networks that are hundreds of layers deep and take weeks to train on hundreds of GPUs. What is it that we can do to make this landscape better? So I've written a little bit of code here, and this was what was giving me trouble with the JavaScript, so I'm just going to hope that it doesn't give us any trouble. I'm going to go ahead and skip this part where I reset the weights from scratch, and I'm going to train a network that can predict handwritten digits. You might have seen the handwritten digits. I think I can actually show them here on my lock screen. Lots of little numbers. Those are the famous MNIST digits. Oh, wrong password. Okay, so it's training. Oh, it's training from scratch. Let's hope the rest of the stuff didn't get reset, because this takes a couple of minutes. Okay, so it started out really bad. 5% accurate, 10% accurate, 22, 35. Okay, so it's learning. Good. This landscape must look pretty good because it's not stopping. And what you learn a lot of times when you're training your networks is that it starts to learn, and then it stops. And then goes down, and then goes up again. And you're like, why is it doing that? Well, I'm going to train this one time in the interest of time and show you. So the way to visualize the weights is that you take all of the arrays that your neural network has, and you create a copy of it and perturb it a little bit like you do in quantum mechanics, and then linearly interpolate between the two. Hope that makes sense. Let's go ahead here and do it in one dimension. So this should go fairly fast. The other one goes a little bit slower. Now, what do we imagine it looks like? This is a very small network that I chose to train on. It has 1 layer, 2 layer, 3 layer. Convolution, convolution, and dense. Convolution is just a kind of layer that understands when things are close to each other. So let's see what the plot looks like. That's not so bad for a newly trained network. You really want to look at the loss on a network that's finished training. But obviously, this network learned very quickly, so the loss landscape couldn't be too complex. Let's go ahead and run this on 2 dimensions. And this takes a couple of minutes. So I'm going to let this run for a couple of minutes and show you something else, and then we'll turn back to it. Because this is this only came up last year, and me and many people have been thinking about this, but it wasn't entirely clear how to draw it in an efficient way. So we'll go and look at that. In the meantime, I would like to challenge you all to do some machine learning hacking. Here is a hard problem. Let's go ahead and maximize that. Train a machine learning model that can solve a Rubik's Cube. I'll give you a hint. There's no profound mathematical knowledge required to come up with the solution to this. And yet, it was extremely difficult for many years to figure out how to solve it. So let's start with what I said before, the loss function. How do we define the loss function? How do we tell if this suggestion from the model is good or bad so that it can continue improving? It's not entirely evident to me from that part. And how many people know how to solve Rubik's Cubes? I imagined it would be a couple of people in the room at least. So I only know the beginner ones, like the 8 sequences. But even knowing group theory and stuff, well, I guess that's a hint. Perhaps the first way to do it, let me just clarify why it's difficult. The difficult part is because there is only one good state that we recognize, and that's the solved state. Every other state other than that is basically crap, except for the ones where you're really close to being solved. So, you know, I just mentioned group theory. You can define it in terms of group theory and homomorphisms between groups and that kind of stuff, and maybe you can figure out how to solve it, you know, with a really hardcore heuristic solver. And so the model gives you an answer, and then you can solve it from there and tell it whether that answer was good or not. But then you did all the work. What's the point of having a machine learning model if you have to do the work? The whole point of machine learning is that it's supposed to do it for you. Okay, so this is where I sort of differentiate between the pure theoretical style and the style that I advocate, which is perhaps more engineering inspired. So this is the way I would solve it. And it turns out this is sort of how they solved it as well. So we have a Rubik's Cube here, and I can rotate it. I'll rotate it once. I'll rotate it again. Okay, I'm going to do a move here now, and I want you to tell me if... I want everybody that thinks this is a good move to raise their hand. Okay, so most people thought that was a good move. Not everyone. And boom, it's solved. So that was a pretty good move, I think. I sort of skipped ahead here because that's a little bit of a giveaway for how to solve this problem. It just occurred to me that solving a Rubik's Cube that's like this is not very hard. And like that, it's not very hard either. I'm going to make life easy on myself. I know the lecturer told me to make a model that can solve a Rubik's Cube, but he didn't say how mixed up it had to be for me to solve it, right? So it actually turns out that that's how the students did it. And they made a model that was quite complex in terms of what it could potentially learn. And they started by teaching it how to solve from one move away from solved. And it learned that quite quickly, as you might imagine. And then right up, once it knew that one, it would always recognize this position. So when it saw this, it knew that it was only one move away from winning because it was here and it could get to a state that it recognized from before and then solve it again. So now we're training a model that knows how to solve 2 moves. And then just keep going, the principle. That wasn't a hard principle, was it? So the loss function here is simply a graph of moves from a solved state. You start from a solved state and then scramble it. And you have a graph backwards that you don't have to solve because you were the one that scrambled it in the first place. And then you can have the model learn one step at a time outwards. And that's how they trained it. So here we have, let's go ahead and scramble this cube here. I don't know how many of you have read about Rubik's Cubes late into the night, but people argue about what the fewest number of moves required to solve a certain cube is. And it's somewhere between, I don't know what the latest number is. I'll just say 17 and 30, something like that, right? So 22 moves would be outstanding. So this model that they made can solve every combination that they've tested in less than 30 moves, which is quite spectacular. And it was done using zero deep theoretical math knowledge or anything. It's just a graph and thinking backwards in terms of the loss function. This is something everybody in the room could have done because you all have the ability to think in terms of geometry, in terms of what is the reward that we're actually looking for and that kind of thing. So let's go back and hope that this little code has finished running. Yes, it's finished running, and I will scroll down, and I hope it looks really nice. No, it didn't look exactly what I wanted it to look like. Well, it's because I didn't train it long enough. But you see that there's a steep hill that it's going down from, and that's what it went down to. So obviously, we're not sure that now, after one set of training, that it's reached the global minima, because as you might imagine, this curve here could very well go over here and then go down or something. We don't know yet. If we train this one more time, we'll end up with another shape that's more convex like that. Concave, sorry. But the big question is, with these super complex neural networks, they don't always, keep going down like that. They start going down and then they go up and then they stop. And you know that it should be learnable, but it doesn't learn. And why is that? And that's because I've prepared this picture. The landscape looks a little bit more like this, which is pretty cool. This is, I think this is ResNet, a very big network that's 150 plus layers deep. And it has a landscape here, and when you're trying to minimize the error of your model by sweeping over parameters, this space, by the way, is not two-dimensional. It's obviously n-dimensional, so as many parameters as you have as input. So if you're looking at a 300 by 300 pixel image, you have like a very multi-dimensional manifold. So this is just a 2D projection. But there is obviously a minima somewhere where the model becomes really, really good. But before it reaches there, the spaceship has to navigate these hills of inaccurate results and try to make it to the bottom. So the university people realized that the errors from the earlier layers were not making it to the bottom and allowing the model to navigate downwards as well as it could. And so skip connections were born. And a skip connection network looks like this. Wow. And it learns very fast compared to a regular neural network. The funny part is that these people only had an intuition of the geometry in their heads. They didn't have these pictures. Now we have these pictures, and we're like, yeah, I knew that. But it does look cool, doesn't it? And it took a long time to generate these pictures. So if we circle back a little bit to what we've gone through, I know this session wasn't long enough to make you all deep learning experts. But what I hope that you can take away from this is that deep learning is pretty special. It can learn basically anything. I spoke to a PhD quite recently who's very talented at machine learning, and I got surprised that one thing didn't occur to him. He was saying the mouse driver in Linux is really bad compared to the mouse driver in OS 10, and he was running Linux on his MacBook. And I was like, why don't you train a model to copy it? And all you would have to do is connect to the driver and see and pull what the input is from the synaptics or whatever the device is, and then check where the cursor position is. And you have a universal function approximator that takes the inputs and gives an output. And it hadn't occurred to him to model the problem in that way. But that's not a profound way of thinking about things until you think of them more in childlike terms, like navigating through lost space through a spaceship, or solving a Rubik's Cube by coming up that you can solve it backwards. So if there's something I want you to take away from today is that, yeah, take the time to learn Keras, learn TensorFlow, learn all the mathy stuff, but make sure that you understand things not in terms of prior conjugates, of distributions, of sampling of this and that. Think of it in terms of stuff that comes naturally to you, in terms of geometry, in terms of fitness, of rewards, and that kind of stuff. And that's when you will make the big breakthroughs. Thank you very much. That's all I had. And if you want the code for this stuff, I'll have it up on GitHub. Feel free to write to me, and have a nice rest of the day.